This video is about electron configurations. Now, before we get too far into electron configurations, it's helpful to think more about how orbitals fill. Our principal quantum numbers correspond to the row the elements in on the periodic table, like 1, 2, 3, 4, 5, 6, and 7. So it corresponds to the row or the period number on the periodic table. Right? Remember, the row itself is called a period, and those numbers 1 through 7 tell us for sure, what s and p orbitals are filling. Now, if we start on the periodic table and we move across these rows, and then down to the next row when we need to, if we're trying to find a particular element, let's say at the beginning of the 3p, we can see all of the electrons that will be in that element. They'll be in the 1s, they'll be in the 2s, we'll fill the 2p, we'll fill the 3s, and then after the 3s, we'll fill the 3p till we get to our desired element, and then we'll stop. So what this really means is that the periodic table is organized in these blocks, and these blocks tell us about the orbitals that are filling. So the first two columns, the alkali and the alkaline earth metals, plus helium. So notice what I did there. I kind of like got rid of helium over on the right-hand side of the table, right? If I'm over here, I sort of took helium and said, wait a second, let's cover that up. And let's go ahead, and I'm kind of popping that out on purpose so we can't really see it. Let's bring helium over beside hydrogen. That puts helium over here with the other electron configurations that end in S. It's going to end in S. It doesn't put it over here, above neon where electron configurations end in P. Okay, so if we move helium over to be beside hydrogen, then all of the alkali and alkaline earth elements plus hydrogen and helium's electron configurations all end in S. We go over to boron all the way to neon. These columns 3 through 8, the 3A through 8A, their electron configurations all end in P. And then if we go to the middle, to those transition metals, their electron configurations all end in d orbitals. And then if we go down to the inner transition metals, those all end in F. And so we call these the S, P, D, and F blocks on the periodic table for where they are filling electrons at the very end of getting all of their electrons. So what are we talking about? Well, these are called electron configurations, where we're going to show the number of electrons in each occupied energy level and in each sublevel. Orbital diagrams are ways that we often represent these. So we often represent an orbital as a box and the electrons in that orbital as arrows. And the direction of the arrow represents the spin of the electron. Remember, I said that electrons are charges spinning on their axes, and you can have one spinning up and one spinning down, and then they'll be attracted to each other. Now, if you get a third electron in there, it'll invariably have the same spin as one of the first, and it'll be repelled. So electrons do spin on this axis, generating their own magnetic field. And when two electrons are in the same orbital, they've got to have opposite spins. So you can have an unoccupied orbital, you might have an orbital with one electron, you might have an orbital with two electrons, as long as they have opposite spin. They have to have opposite spins. What can't you have then? You can't ever have an orbital with 3 electrons because, these 2 electrons that are pointed up would have the same spin, and so you can't do that. So filling the orbitals in a subshell with electrons, how do we do that? Well, orbitals that are in the same subshell have the same energy. For example, all of the 2p orbitals. they're all at that p subshell, they all have the same energy. So when filling orbitals that have the same energy, we'll put one electron in each before completing the pair. So that's called Hund's rule. Sometimes this one's called the empty bus seat rule. The idea here is if you put a bunch of kids on a bus, let's say for a field trip, and this especially is true with older kids, they all try to get their own seat. And so they're each going to want to try to find their own seat, to go ahead and sort of claim that, if you will. I was trying to make sure we could see these 1S and 2S and 2P. Anyway, they'll try to go and claim that seat. And so we'll put one electron in each bus seat of equal energy. Okay, this idea that an orbital had to have two electrons and they have to have opposite spins, that was called the Pauli exclusion principle. So that's an important one. And again, Hund's rule, that one is sometimes referred to as the bus seat rule. And so this is the idea that, let's say you're at the p orbitals, you have your 2p orbitals, and you have 3 of them, for example. You are going to put one electron in each one. They each get their own bus seat at the 2p level before they're going to want to double up. Let's just do a couple of simple examples to try to help us to first understand what's going on here. Okay, let's find lithium. Find it on a table, find its atomic number. Actually, I think I have a table for us here, so we can do that together. Lithium's right here, it's atomic number 3. That means that it normally has 3 protons, and when it's neutral, it will have 3 electrons. It's got no charge here, so let's assume neutral for now. So if it has 3 electrons, what's its electron configuration going to be like? Well, it's going to put one electron spin up, and then it only has this one other s electron, so it'll put one spin down, because there are no other electrons, no other orbitals at the 1s, no other boxes. Then it will move on to the 2s and put an electron spin up. That will be its 3 electrons. So its configuration is 1s has 2 electrons, so you write that as a little superscript. And then at the 2s, you have 1 electron. And then what you can actually do is count up the superscripts for the number of electrons. So 2 plus 1 gives you a total of 3 electrons. So you count up the superscripts, 2 and 1 is 3. Okay. So let's just rewrite that so that we can really see it. 1s, 2 electrons, 2s, 1 electron, up, down, up. Okay, let's do carbon next. Carbon's atomic number 6. At the 1s, you're going to put 1 electron spin up and 1 spin down. Then you're going to move on to the 2s, 1 spin up and 1 spin down. Now at the 2p, you have 3 orbitals that are all equal energy. They're all 2 and they're all p, so they're totally equal in energy. So you're going to put 1 electron on each bus seat. Because we already have 1, 2, 3, 4 electrons, this is going to be electron 5, and this is going to be electron 6. It's really important to follow that bus seat rule here. So what's our electron configuration? 1s2, 2s2, and then 2p2. So 2, 4, 6 total electrons. So again, we can add up those superscripts to see how many electrons we have. We can go 2 electrons plus 2 more plus 2 more is 2, 4, 6 electrons. So what if we want to know a little bit more about what this looks like? Here is kind of a picture of carbon, so we can get an idea of what we are talking about for carbon, 6 electrons. So first 2 electrons went at the 1s and then 2 at the 2 S. Here are the 3p orbitals. See how they're at the same level? They're equal in energy. First we went from 1s lowest energy, then we went to 2s, next lowest energy. Then we went to 2p, but these are equal in energy, so we have to put 1 in each 2p bus seat before they'll double up. What does that really mean is happening with the electrons, and how do we, sort of translate these boxes to the shape that we were learning about in the quantum mechanical model? Well, what this really means for carbon is that there's this inner sphere, the 1s, that's going to have 2 electrons in it. Then there is the next concentric sphere, the next 2s. That's going to have 2 electrons in it. Then somewhere in this 2px orbital, there'll be an electron, could be in either lobe of it. And then in the 2py, for example, there'll be an electron in there somewhere. And the z, the 2pz, could just be empty. But it gets hard to see where these arrows are in these shapes, and it gets a little confusing. So, that's why we kind of do the boxes or our shorthand notation, because the shapes get a little tricky to think about with the electrons sort of layered onto them. Okay, so let's do some more practice. This says, write the ground state orbital diagram and electron configuration of magnesium. So we need a periodic table, and we need to find magnesium on this table. So magnesium is right here. It's atomic number 12. So that means that it would normally have 12 protons, and if it's neutral, 12 electrons. So number of electrons, 12 electrons. We can draw boxes to place all those electrons. But let's just kind of think it through. We're going to fill the 1s orbital with electrons to get all the way to magnesium. We're going to think about the order of filling. We're going to have to fill the 1s with 2 electrons. Then we're going to have to fill the 2s with 2 electrons. To get to magnesium, we're next going to have to fill the 2p here. So next up, we're going to fill the whole 2p section with its 6 electrons. 1, 2, 3, 4, 5, 6. Now we're at 2, and 2 is 4, and 6 more is 10 electrons. And then to get to magnesium, we'll need to, at the level 3, fill the s with 2 more electrons. Or excuse me, fill the 3s with 2 more electrons. So we've got 1s2, 2s2, 2p6, 3s2. So let's put that down for our electron configuration. We said we had 12 electrons. We had 1s2, 2s2, 2p6, 3s2. Now, we could draw boxes for s's and p orbitals, but that's already done for us. We could add 1 electron to each. So we had 1, 2 in the 1s. We had 3, 4 in the 2s. We had 5, 6, 7. Notice I'm following Hund's rule and I'm putting 1 in each bus seat. Double up 8, 9, 10. And then electrons 11 and 12 in the 3s. So we can look at the periodic table, or we can use boxes. I'm trying to show you a mix of both of these skills for this example with magnesium. Okay, let's do some more examples. This is a great place to pause the video and see how you do with these examples before I do them for you. Did you pause and try these? Give them a try. I think you can do it. Okay, let's find potassium together. Let's move me over here. Potassium has atomic number 19. So if it's neutral, 19 electrons. Now let's just think through the order of filling here. We're going to fill 1s with 2 electrons. We're going to fill 2s with 2 electrons. Then we're going to go over and fill 2p with 6 electrons. Then we're going to fill 3s with 2 electrons. And then we're going to fill all of 3p with 6 electrons. And then we're going to have 4s, and we're going to have one more. So looking like 1s2, 2s2, 2p6, 3s2, 3s2, 3p6, 4s1. Just have to be able to read what I wrote, huh? Okay, so I'm going to copy that down here. 1s2, 2s2, 2p6. That's my first 10, by the way. 2 and 2 is 4, and 6 is 10. 3s2, 3p6, that's 18, and 4s1 is 19. Now, I'm also asked to do the orbital diagram. So I'm going to actually do that down here. I'm going to do 1s and put my 2 electrons, 2s and put my 2 electrons, 2p, I should have 3 boxes, 1, 2, 3, 4, 5, 6. That's my first 10 electrons. Here's electron 11 and 12. This is going to get me 13, 14, 15, 16, 17, 18. And 4s is going to have just 1 19th electron. Okay, so the boxes are sort of supposed to go up here, but I was a little out of room. That's fine. Okay, let's use the table again to find gallium. Okay, so I need to find gallium. It's atomic number 31. So we can look at the periodic table and think through the order of filling. Looks like I'm going to have 1s2, 2s2. Then I'm going to go over to the P block and fill 2p6, and then 3s2, and then 3p6, and then I've got 4s2. Now, when I go to the D block, I have to remember that I go down one number because I still haven't filled the 3D. At the third level, we have 3D, and it's 10. And then for gallium, it'll be 4p and a 1 to get to 31. Okay, so I think I'm going to copy down the configuration. 1s2, 2s2, 2p6. That's my first 10 electrons. 2 and 2 is 4, and 6 is 10. 3s2, 3p6, 4s2. That's my next 10 electrons. So I was at 10 here. 12 plus 6 more is 18, and 2 more is 20, and 3d10 is 30, and then 4p1 will give me my 31. I needed 31 electrons for gallium. Okay, so I'm going to write down a 1s box and put my 2 electrons in a 2s box and 2 more electrons. And at my 2p boxes, I'm going to follow Hund's rule. I'm going to put 1 in each, and then I'm going to double up. There's my first 10 electrons. 3s and 2 electrons. 3p. I always like to follow Hund's rule because it's such a great habit that you want to be in, because when you have a bus at the end of your configuration that needs to be partially filled, you got to fill that partially filled bus correctly. Okay, 3D. Boy, I might be a little squashed here. 1, 2, 3. I'm going to do 4, 5. I'm going to do my fifth one up here. 1, 2, 3, 4, 5. Fill the bus correctly. 6, 7, 8, 9, 10. And then lastly, I'm supposed to have a partially filled P, but I'm out of room for it. Can I put it up here? You're okay with that, right? 4p, because it needs to have 3 orbitals, but only 1 electron. Okay, so let's double check. I've got 1s2, 2s2, 2p6, that's 10. 3s2, 3p6, 4s2, that's 20. 3d10, that's 30, and 4p1 is 31 electrons. Phew, I did it for gallium. I don't know about you, feels like an accomplishment right now. Okay, let's try a couple more examples. Now, these two are a little bit trickier. They're ions. So let's look at scandium, but it's got a 3 positive charge. So we can go ahead and find scandium on our periodic table. Sc is 21. Okay, so if this were neutral, it would have 21 protons and 21 electrons. How do you get a positive charge? Do you remember this? I always like to say, I lost an electron, I lost an electron. Scandium, we'd ask it, are you sure? And it would say, I'm positive, I lost electrons. Okay, so you have to lose electrons to get a 3 plus charge, and you got to lose precisely 3. So if I lose 3 electrons, aren't I down to 18 electrons? Okay, so I'm going to be drawing the electron configuration for actually 18 electrons, not 21. Okay, so 18 electrons is going to be 1s2, and then it's going to be 2s2, so I'm just filling these in order, and then it's going to be 2p6, and then it's going to be 3s2, and then I better check. I'm already at 10, 12. I only want to get to 18. Gosh, that's just the 6 more right here. That's 3p and 6, right? And that will get me to 18. Okay, so that's my 18 electrons. Now, by the way, 18 electrons is right here at argon. Notice how that's a noble gas. Elements like to gain or lose electrons to be like the nearest noble gas. So scandium doesn't want to have to go all the way over to be like krypton. It wants to just lose a couple electrons to go back and be like argon. And the reason is going to be to have filled outer shells of electrons, to have exactly a filled 6 electrons, rather than having, for scandium, rather than having a 3D with just one lone electron, it would rather have this filled 3p6 that's all filled up with electrons. Okay, so let's rewrite this. 1s2, 2s2, 2p6, 3s2, 3p6. It's about having this third level exactly filled, the 3s and 3p. That's really perfect for scandium. So I'm going to do the boxes down here. Because again, I'm kind of out of room. This pen writes really big. 1, 2, 2s will be 3, 4, 2p. We'll fill it with 5, 6, 7, electron 8, 9, and 10. I've got 10 electrons there. At the 3s, I'll get electrons 11 and 12. And at the 3p, I'll get electrons 13, 14, 15, 16, 17, 18. Okay, and we're going to learn that there's something pretty magical about getting everything all filled and being like the nearest noble gas. Okay, I meant to erase all that, because there's too much on the screen there. Let's look for the fluoride ion. Okay, so fluorine's right here. A neutral fluorine is normally going to have 9 protons and 9 electrons. How does it become F minus? How does it get a -1 charge? Well, it had to get extra electrons. It must have 10 electrons. Gosh, if it had 10 electrons, it's trying to be like neon. The same way that scandium was trying to backtrack and be like argon, fluorine is trying to move forward and be like neon or its nearest noble gas. Okay, so what's the configuration there? We'll fill the 1s. It's 1s2. Then we'll go and fill the 2s, 2s2, and then we'll fill the 2p, 2p6, and that should get us to 10. So we've got 1s2, 2s2, 2p6. And so we'll have our 1s have 2 electrons. Our 2s will have 2 electrons. We're at 4. And at 2p, there's 3 different 2p orbitals, 5, 6, 7. Notice how I'm following the Hund's rule, 8, 9, and there's our 10th electron. So there are our 10 total electrons, and we're getting to be like neon, that nearest noble gas, with exactly 10 electrons. Okay, so let's try a few more examples. This is a great place to pause and try to write these 3 electron configurations. Go ahead and pause now and try them. Okay, so let's do aluminum. It has 13 electrons. So let's see. We might also want to write these down. Manganese is going to have 25 electrons. Oxide, well, oxygen has 8 electrons normally. How did it get to be 2 minus? Well, it had to get 2 more electrons. Plus 2 is going to be a total of 10 electrons for the oxide. So 2 and 8 is 10. Okay, let's look at aluminum first. We're going to fill the 1s2. Then we're going to come down and fill the 2s2. Then we're going to go over here and fill the 2p6. And then we're going to fill the 3s2. And then we're going to put 1 electron at 3p and a 1. So tempting to put that 6 at the end because we're just so used to doing that. So if we want to write this one again, we can write it a little neater. Let's not forget the 25 we had and the 10 electrons. That's going to be helpful. Aluminum was 13, by the way, and it was 1s2, 2s2, 2p6, 3s2, and then we have 12 right there, and we need 3p1. It takes everything in my power not to write 6s for all those p's to stop myself. So something I suggest, really working on too. We could start writing out manganese. 1s2, 2s2, 2p6, 3s2, 3p6. That'll get us 18. 4s2 will get us 20. And then if you'll recall, oops, we might have to go back. So we have our periodic table. After we fill the 4s, we actually go down to the 3d. And manganese is not going to fill the whole 3d. So we won't want the whole thing filled. Right now we're at 2 and 2 is 4 and 6 is 10. 2 more is 12. 6 more is 18. 2 more is 19, 20. So we're at 20 electrons right here, and we just need 3d5 to get to 25. So, we filled the 3s, we filled the 3p, we go down and fill 4s, but we've got to hop, drop back from 4 to 3d. Okay, and the oxide with the 10 electrons, well, we kind of see how to fill the first 10. We remember that from just even aluminum. 1s2, 2s2, and 2p6 gives us 10 electrons. Again, oxygen's trying to be like the nearest noble gas. Neon's got atomic number 10, and so oxygen wants to be just like that neon and get to atomic number 10.